molecular formula. But different structures or structural formula or spatial orientation. Different structures means that the bonds are connected differently, and those gives rise to structural isomers, and structural isomers are sometimes called constitutional isomers. They have the same formula, the same molecular formula, but bonds are connected differently. Or spatial orientation, the same structural formula but arranged differently in space. So this gives rise to what we call, and over here certainly we're talking about stereoisomers. And you'll come across words like conformational isomers, such as and these we talk about cis-trans isomerism. Also we can talk about Newman projections, where we have eclipse or staggered conformers. Or you can also talk about gauge or anti-conformers. So cis-trans or eclipse or staggered or gauge or anti or stereoisomers, and they are also conformational isomers. And then on the other side we will also be talking about enantiomers, which are also stereoisomers, that are mirror images of each other. And stereoisomers that are not mirror images of each other are called diastereomers. And then we will also talk about configurations like RNS configuration. You'll apply to a situation where you have chiral centers in a molecule. And then we also were talking about EZ. So this all summarizes isomerism. C4H 2n plus 2 will be 10. Obviously this will be butane, but we can find butane isomers or compounds that will have the same formula C4H10, but the structure will be different from a normal straight chain butane. So straight chain butane will look like this. Let me draw the structure C. This is butane. 1, 2, 3, 4 carbons with 10 hydrogens. What I need to do is to draw another structure. Okay, this is 2. Can maybe write 3 here. Okay. Now I'm going to, instead of putting all the carbons in straight chain, I'm going to put another carbon here. So far as the carbons have 4 bonds connecting to 4 different atoms, it's fine. We still have an alkane and it's saturated. Now let's put our hydrogens here. So this satisfies what we call structure isomer. We have 1, 2, 3, and this carbon is branch on carbon number 2. Obviously this is a substituent. It's carbon and 3 hydrogens, so this is a methyl group, and the longest chain is 1, 2, 3, or 1, 2, 3. If this side is the longest chain, this will be a substituent. If this is the longest chain, this will be a substituent, and vice versa for that one. Okay. So the name of this compound right here is 1, 2, 3. So it will be like propane. Then carbon number 2 is having a methyl group, so 2 methyl propane. And this is obviously different from this, to have different physical properties from this, because it's a structure isomer. It will not behave exactly the same as butane, but to have the same chemical formula, C4H10. So 2-methylpropane is a structure isomer of N-butane, normal butane. Let's look at this. So CnH2n plus 2 gives 14 for hydrogen. Let's write open structure of this. So this 6 carbon is a normal hexane. Okay. Now, because we have lots of carbons, that means we can also get a few structure isomers of this. So a way to write structure isomers is just try to shorten the carbon length and then put the other carbon as a substituent, one of the middle carbons or one of the carbons inside the chain. So let's see, I'm going to shorten it by 1, so let's see, we have 2, 3, 5, okay. Let me put on the skeleton. Alright, so now we have 5 carbons in chain. Now, where will the other carbon go? I can put it here, or here, or here. I will also get a substituent, so let me see. So the longest chain 1, 2, 3, 4, 5. So this is pentane. That's the parent's name will be pentane. Now there's a substituent on carbon number 2. Call this carbon number 2 and not carbon number 4, because I'm starting the count from here. 1, 2, 3, 4, 5, and not 1, 2, 3, 4. So this is 2 methyl pentane. The same name will apply if this methyl group wasn't here, but if it was here, the name will still be the same. If I change the structure slightly, maybe I put it here, but I put the CH3 group here, then the name will be different. It is 1, 2, 3, 4, 5, or 1, 2, 3. So the name instead of 2 is going to be 3 because carbon number 3 is bearing the methyl group. So this is a structural isomer of hexane. Now I can get other structural isomers by further shortening the carbon length. Alright. So I have 1, 2, 3, 4. So I'm having a butane right now as my parent's name, and I can put the substituent here CH3 just to get the number of carbons to match hexane. So I have 1, 2, 3, 4, 5, 6 carbons and then 14 hydrogens. Okay. Now let's try and name this. 1, 2, 3, 4. So butane, parent's name. Now on carbon number 2, 1, 2, and not 1, 2, 3. No, 1, 2. Carbon number 2 is bearing 2 methyl groups. So you write 2, 2 dash, and dimethyl 2, 2 dash dimethyl butane. It's a structural isomer of hexane. I can change this structure slightly by instead putting a hydrogen here, but putting a methyl group right here. That is CH3, but right now they are not on the same carbon, so I cannot use this name. The parent's name is butane. However, carbon number 2 is bearing a methyl group, carbon number 3 is bearing a methyl group. So to write the name, you can write 2, 3 dimethyl butane, and this is a structural isomer of hexane to have different density and other difference in physical properties from hexane. Cyclopentane have 5 carbons and 10 hydrogens. 6. Let's try and see if this will give us something. So we have 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this doesn't give us 14. So obviously a cyclic structure like this cannot be a structural isomer of hexane and hexane. Even cyclohexane is not a structural isomer of hexane, because cyclohexane is C6H12